Hello, welcome back to the Geography 300 Geographical Data Analysis video series for WVU. We're now picking up from the probability terminology from the previous video, continuing on our path, as it were, towards inferential statistics, now looking at some of the mathematical rules of probability, and especially relating two things to another. So first, just some shorthand. I will be using here, and it is very common to use P of A. P with A in parentheses as the probability of outcome A, just to make our notation easier, make life easier for us as we look through and read through these things. The first rule, remember, it is the probability, or the probability is the frequency of that outcome divided by the frequency of the event which could have led to that outcome. That means it has to be between 0 and 1. Something that is completely, truly impossible has a probability of 0. Its outcome is 0. Its frequency of the outcome is 0. No matter how often that event can happen. So, the probability that we can have an election every 4 years, there are several of them during his lifetime, the probability of Arnold Schwarzenegger becoming president is 0, because he doesn't meet the criteria to become president. He is not a natural born US citizen, he is born in Austria. So that is an outcome, President Arnold Schwarzenegger, which is well and truly impossible. It has a probability of 0. If something is absolutely guaranteed, the probability of there being a sunrise today, that is guaranteed to happen. It may be behind clouds, it may be behind snow, but it's going to happen. There will be a sunrise. That outcome, yes, there's a sunrise, happens every single day. It is a probability of 100%, or 1. If you're used to dealing in percents, multiply by 100 for the percent. Cent, after all, coming from Latin 100. 100 per 100 is a probability of 1. 50 per 100 is half of that 100. 50%, 0.5, 1/2 as the probability. Now we can start to look at different events happening in a sense concurrently, or we'll be looking at them at the same time. And we can have two different ways of looking at the looking at two events happening together. We can ask, is it the case that they both happen? That would be the probability of A and B, or what's called the union. The symbol here is something that looks a lot like an uppercase U for union. The other way is the intersection, which is PA intersect B, and that's the upside down version of the union. It looks a bit like an N, lowercase n, so that's how you might remember it's the intersection. And it's the case that either A or B happens, or both. If both is a possibility, then that goes in there too. Counting up, we'll now look at the math behind these two, and then get to a third one. I'll write it down here. If we know the outcome of one of these, I put it so that there's A, and then we want to know, given that A already happened, given that we already have that outcome, what is the probability of B? We'll start by looking at the union. The probability of the union of two things, in some ways that can be extremely difficult to work with. It makes our life easier if, and only if, we know they are independent. This actually can then be used as a way of checking independence. The probability of the union of A and B is simply their product. The probability of A times the probability of B, if and only if. And that's what this if with two F's means. If and only if they are independent. If they are not independent, if A makes B more likely, it will be more than this. If A makes B less likely, it will be less than this. The calculation for independence And you might be thinking, probability of A plus the probability of B, okay, that is something that kind of makes sense. So I want to see if either A or B happens, I just add them together. We have to account for the intersection, or the union. We have to account for that case where both of them happen at the same time, and basically that combined event is double counted. So I have to subtract off the union. This is true regardless of independence. So to illustrate both of these, I can think of, I'll pull a couple examples from a deck of cards. The probability of red. So I pull a card out of the deck. How likely is it that it's red? Well, assuming I've taken out the joker, there are 52 cards, 26 or half of them are red. So that's a half. The probability that it's a face card. So think about how many face cards there are. 3 per suit times 4 suits, the jack, queen, and king. That's 12 out of 52. Which, if I wanted, I could take that down to divide the top and the bottom there by 4, and I get 3 out of 13. Since in a standard deck of cards, red face cards are just as likely as black face cards, it's 3 per suit. And we don't have any, and each suit has the same number of cards. Strangely enough, there are decks for which that is not true, but for a standard US deck, that is the case. So these would be independent. You can think of that. There are a grand total of 6 red face cards out of 52. So our frequency of a red face card is 6. The frequency of all cards, 52. That can serve as a check on this probability. If I divide this by 2, I get 3 out of 26 to reduce both the top and the bottom. To reduce the fraction, that is indeed 1/2 times 3 over 13. So there we can confirm those are indeed independent events. I'll use the unreduced here. To begin with, there are 26 red cards. Add in the 12 face cards. But, for example, the Queen of Hearts is red and is face. So if I'm counting up, I now have counted it both times. And that's true for any red face card. So, as I said, I subtract out the red face cards. And I get 32 cards are red or face, or both. So now for how we get to conditional probability. That would be as I said, I'm going to put it here, the probability of B if we knew A already happened. So it's the probability of both divided by the probability of A in the first place. So to take that example from the previous video, the probability of dying, conditional upon falling out of a skyscraper. So the probability that both happens divided by the probability of falling in the first place. Both of them are very unlikely, but they're pretty much the same. So that might be almost one. You know, there might be, say, a fire crew out there with one of those big trampoline things to catch you if the building is on fire and you are intentionally jumping out onto the trampoline thing to save your life. It is not completely impossible to survive that fall, but incredibly unlikely. So I would, just off the top of my head, estimate that as 0.99 of one conditional upon the other. There is one more small rule. It does show up as something that can be useful going forward. And this is, in many cases, we will want to have our outcome defined in such a way that it's binary. As here, either you live or you die. The probability of A not happening in that event, or the probability the outcome of the event is something that isn't A, plus the probability that the outcome is A, must equal 1 or 100%. This comes in handy because we may, even though we might be interested in outcome A, it might be a whole lot easier to figure out the probability it doesn't happen, and then subtract that from 100% or from a probability of 1 to get back to the probability of A. I might illustrate this in our class Zoom session, depending upon how many people have questions, using something called the birthday problem to find the probability that two different people in that room share the same birthday. So those are different probability rules, getting into some of the math of probability. As always, thank you for watching. Have a good one. And if you have any questions, please speak up in the class Zoom session or by email.